Welcome. So in this series of podcasts, we're going to learn how to graph exponential growth and decay functions and logarithmic functions. But first, we're going to learn a little bit about exponential growth and decay. So exponential functions. A function is called an exponential function if it has a continuous growth factor. This means that for a fixed change in x, y gets multiplied by a fixed amount. With linear functions, we would add the same amount each time. This time, we're going to take the previous amount and multiply by the same amount each time. So our growth is going to be much faster, or our decay is going to be much faster than we would see with a linear function. So an example, money accumulating in a bank at a fixed rate of interest increases exponentially. By the way, it shouldn't be too hard for you to figure out what to fill in your notes because they're either underlined or they're in another color. All right, so now we're going to look a little bit more at exponential growth. There are many quantities that grow exponentially. Some examples are population and compound interest. An understanding of exponential growth is essential if you want to be comfortably rich later on. The special thing about exponential growth is that the rate of growth increases as time increases. Right? So it's a very fast rate of growth or a fast rate of decline. The curve gets steeper as time goes on. Right? So here we have an example, and this it doesn't even quite show how quick the growth is because of the scale that's on the x-axis. But if we invest $1,000 at 8% interest, it grows to almost $5,000 after 20 years. Right? So if this were a linear function, it would not grow nearly that fast. So let's learn the parts of an exponential equation. So an exponential function has the form f of x equals ab to the x. You should probably underline that. A cannot equal 0. Right? A is your starting value. Right? Let's actually underline that. I believe it's already filled in your notes. That's your starting value. It can't be 0. You have to start with something for it to grow, right? If you have nothing, it won't grow. If there is nothing written in front of the number that's raised to a power, then it's understood to be 1. So if the base has no coefficient, a is understood to be 1. You have to start with something. B cannot equal 1 because 1 raised to any power would be 1, which is a constant function. B cannot equal 0. 0 raised to a negative exponent would put 0 in the denominator and be undefined. So this is already in your notes. By the way, the red words need to be put in your notes. But you already have this in your notes, right? So we can plug in positive and negative numbers for our exponent, right? If I raise 0 to a negative number, right? The negative makes it the reciprocal. That would put 0 to the nth in the denominator, and division by 0 is undefined. You can't take something and divide it into no groups, right? That's undefined. And finally, b cannot equal negative numbers because even roots of negative numbers would not be real numbers, right? They would be complex numbers. Right? And we will not be dealing with complex numbers when it comes to exponential equations. Right? We dealt with complex numbers with quadratic and polynomial, but not with exponential. Right? So for instance, if we had 16, and this is in your notes already, if we have 16 to the 1/2 power, we know that 1/2 as an exponent equals the square root. And the square root of negative 16 is not a real number, it is a complex number, and no complex numbers for exponential equations. If b is greater than 1, the graph of f of x equals b to the x will increase from left to right, and it's called exponential growth. Right? So no matter what, b cannot equal 1. Right? And it has to be greater than 0. right? We already went through that. But if it's greater than 1, it's going to be exponential growth. If it's between 0 and 1, the graph of f of x equals b to the x will decrease from left to right, and it's called exponential decay. Right? So base greater than 1, your graph grows, increases from left to right. If your base is between 0 and 1, your graph declines. It's going to decrease from left to right. So now we've looked at the structure of the equations a little bit. I'm going to add one little thing to that structure. Sometimes you're given an equation, and sometimes you're not given an equation. You're given the rate of growth or decay, especially in the next series of lessons where we'll be solving equations. And so I wanted to take the time to go over that. So the base given as a rate of increase or decrease. Right, so here we have for growth, y equals a times 1 plus r to the x. The 1 plus r is the base, right? That's the same as b, as base. If it's decay, y equals a times 1 minus r to the x would be decay. And the 1 minus r, again, is your base. A is still the initial amount, right? Before we've done anything else, that's our initial amount. R is your rate of growth or decay. It's often given as a percent, and you'll need to change to a decimal. We won't see this too much in this particular lesson, other than we're going to be just identifying rate of growth or decay. But we'll see it in the next lessons, so I thought this is a good time to go over it. And then x is the number of time intervals that have passed. When we're graphing, x is just going to be whatever our x value is, right? But in the next series of lessons where we're solving, we're going to be solving for time. And so then x is going to be equal to time. Right? So if we're adding something to 1, and it's always going to be a decimal. It could be a decimal that's greater than 1. Nobody says that our decimal has to be between 0 and 1. Right? We could increase by 500%. Right? And then we're going to be adding 5. Right? But here, 1 plus r is going to be greater than 1, right? I'll put that in there. So 1 plus r will be greater than 1 is what I meant to put in there. Greater than 1, so that will be growth. Over here, 1 minus r is going to be between, it'll still be greater than 0, but it will be less than 1, all right? So that's why this one is decay. I think I'm going to move this over a little bit. That's why this one is decay, and this one is growth. Oops. The last thing we're going to do in this lesson is actually just identify the difference between growth and decay from an equation. We'll also just take a quick look at what an exponential growth equation looks like, just to kind of give you an idea of what's coming up. And I think that's next. Okay, so you should have this in your notes, but this is not in your notes. All right, just kind of gives you a little idea of what it's going to look like. So the table and the graph show an insect population that increases over time. All right, so here's our equation. F of x equals 2 times 3 to the x. The number that does not have the exponent on it, that's your starting population. Okay? You have to start with something. In this case, we're starting with 2 fruit flies, which is good because if we just had 1 fruit fly, I think it would have a really hard time increasing this population. 3 is your base, right? In this case, this is growth because it's greater than 1. How much growth? Well, actually, we're increasing. So if you remember that our base can also be thought of as equal to 1 plus r if it's growth, and 1 minus r if it's decay. Right? So if 3 is equal to 1 plus r, because 3 is our base, that would mean that 2 is our rate of increase. What does that mean? When we talk about rate of increase, we're going to talk about it as a percent. So if it's 2, 2 is equal to 200% growth. Right? 1 is 100% growth, 2 is 200%. Right? If it was 0.5, it would be 50% growth. Right? So each time we're having 200% growth because our base is 3. If our base is 3, that means that we could find the next number in the sequence by multiplying by 3. Right? So if we didn't have the table filled out, and let's just say we didn't know how to raise a number to a power, we could just keep multiplying the starting population by 3 each time, and that would give us the next number in our sequence. Or we could just plug into the equation. Right? So for instance, if I wanted to know how many fruit flies there'd be after 4 days, I'd take f of 4, which would be 2 times 3 to the 4th. Order of operations, exponents first. Right? Don't make me sad. Exponents first, then multiply. It is not 6 to the 4th power, it is 3 to the 4th power times 2. So that would give us 2 times 3 to the 4th power is 81, 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81. So 2 times 81 would give us 162 fruit flies. And if you were to multiply 54 times 3, you'd get 150. Right? 50 times 3 would be 150. 4 times 3 would be 12. So you'd have 162 fruit flies. Right? So 2 different ways. Generally, it's easier just to plug in, especially if you don't want to find every number of fruit flies that came beforehand. Because if I said, okay, how many fruit flies was there on the 100th day, I don't think you'd want to find how many fruit flies there were on the 2nd day and the 3rd day and all the way till you got to the 100th day. Right? But you could do it that way. Here, if we connect our points, which is what we'll do when we graph, right, we can see how quick that rate of increase is. By the way, it would keep going this direction. However, negative time has no meaning. So if we're graphing, yes, we're going to have it keep going that to the negative direction because we can have negative numbers for our exponents. But if we're talking about fruit flies, right, there's not going to be negative time. So a function rule that describes this pattern above is f of x equals 2 times 3 to the x. This type of function in which the independent variable appears in an exponent is called an exponential function. That's why it's called exponential function. Your variable is always an exponent. Notice that 2 is the starting population and 3 is the amount by which the population is multiplied by each day. Right? So just a little introduction to what exponential graphs are going to look like. In the next lesson, we'll graph them. In this lesson, we're just going to be looking at rate of growth, starting population, what's our base, is it growth or decay, etc. Right, and moving along. There we go. I think this is the last page in the notes. In the last page for this particular lesson, this particular podcast. You've got more notes, but that will be in the next podcast. I have this all in your notes. Everything you see up here is in your notes. So we're going to fill these in. And actually, I'm going to make one tiny little change. I'll make it right there, and I'll fix your notes before I give them to you. And that is, I'm going to get rid of that. Yeah. There, now I've got every pretty much every kind of equation I can think of. Got to work on that spacing a little bit. But let's go through these. So recognizing growth and decay functions from the equation. If the factor b is greater than 1, then we're going to call the relationship exponential growth. If the factor b is less than 1, and let's clarify that, it's between 0 and 1. I'll fix that in your notes since I already have to fix one thing. We call the relationship exponential decay. All right, so we're going to state whether f of x is an exponential growth or decay function. We'll explain our answers and then state the rate of growth, decay, and the initial amount. In your weekly work, you'll have something very similar to this. You can model your answers off of my answers. All right, so let's look at our first one. And actually, while we're going through these, you think in your head whether it's growth or decay. All right, we'll practice. All right, so the first one is decay. If you thought decay, you were correct. That's because our base is equal to 1/3, and 1/3 is between 0 and 1. So this would be rate of decay. So let's circle decay. Rate of decay is going to be 1 minus 1/3. So that's going to be 2/3, right? So our rate is always 1 plus or 1 minus, right? So this one is decay, it's going to be 1 minus. So we're decaying by 2/3, right? That's how we got to the 1/3, right? So if we're decreasing by 2/3, our base is going to be equal to 1 minus 2/3. That's what gave us the 1/3, right? That's how you figure out your rate of increase or decrease. If we want this to be a percent, by the way, we would have to round it a little bit, and it would be approximately, that's about 60, it'd be 66.7% approximately, right? Our initial amount, which is why I took off the -4 there. I wanted us to think about it. What if there's no number up there? Then the initial amount is 1. All right, let's look at the next one. F of x equals 2 to the 0.15, 2 times 1.5 to the x. This would be, you think in your head, is it growth, is it decay? Is it growth, is it decay? It's decay, because your base is 0.15, and 0.15 is between 0 and 1. This would be a rate of decay, and the rate of decay would be 1 minus 0.15. So that would be 0.85, which is equal to 85%. Should have moved initial amount over a little bit and given me more space. But I did the same thing to you. So the initial amount is right here in front. The number that's not raised to a power, the initial amount is 2. All right, f of x equals 7 times 5/2 to the x. Is it growth? Is it decay? Think in your head which one you think it is. If you said growth, you were correct, because your base is 5/2, and 5/2 is greater than 1. I don't know why I gave myself such a long line to write that. So this time it's going to be, let's circle rate of growth, right? So the rate of growth, so to get to 5/2, right? So our base here is 5/2. We would have had 1 plus something equals 5/2. One plus r equals 5/2 because it's growth this time. Right? It's easier to figure out, I think, on decay. Right? If I have 0.15 there, I was decaying by 85%. So here you got to think that if your base was 1, which you can't have because then you wouldn't change, that 1 would keep you just the same. So it's the same plus some amount more, which got you to 5 halves. 1 is the same as 2 halves, right? So 2 halves plus r is 5 halves. That means r is 5 halves. Excuse me, is 3 halves. Yes, I can subtract 5 minus 2. 3 halves. So r is 3 halves. As a percent, that would be 1.5. That's 150%. I so should have made that line a little bit longer. Sorry for you having to cram it in as well. So you're increasing by 150%, right? Because the 2 halves just keeps you the same and doesn't change you. The 2 halves plus 3 halves gives you 5 halves, and that's an increase of 150%. If this part's a little tricky for you, it will get easier when we're solving. And matter of fact, this is the only time we're really going to be dealing with rate of increase or decrease in this particular lesson. But I thought it was a good time to talk about it before we got to the next series of lessons. Your initial amount is just the number that's not raised to an exponent, so that is 7. All right, let's look at the next one here. All right, so f of x equals negative 4 times 3 to the x. Is it growth? Is it decay? It is growth. This is just like the fruit fly problem. Because your base is 3. And 3 is greater than 1. So this is growth. Let's circle growth. There we go. Your rate of growth is, all right, so 1 plus r gave you 3. You subtract 1 from both sides, r is 2. That means you're increasing by 200%. 200% growth. Your initial amount is the number not raised to the power, negative 4. Yes, you can have a negative starting value. And finally, the last one, f of x equals 3 to the 1 times 1/4 to the negative x. Be careful, this is in your notes, put a little star. If x is negative, rewrite the equation by simplifying the negative exponent. So this is the same as f of x equals 3 times, okay, so you got to flip it. Instead of 1/4, it's going to be 4, and make your exponent positive. 3 times 4 to the x. So is this growth or decay? Dun, 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 dun. It is growth, because your base is 4. 4 is greater than 1. Oops, I'm no longer purple. 4 is greater than 1. Your rate of, let's circle growth. All right, so 1 plus r equals 4. That means r is 3. You're increasing by 300%. So your base is 4, because you get your base by 1 plus the rate of increase, or 1 minus the rate of decrease. Right? So 300% growth, your initial amount is the number that's not raised to a power. Your initial amount is 3. And that's all there is to understanding exponential growth and decay equations. All right? Thanks for watching this one. In the next lesson, we're going to be looking at graphing exponential growth and decay. Bye for now.